Functions in Python are first-class objects, meaning they can be assigned to variables, passed as arguments, and returned from other functions. This flexibility allows for powerful patterns like decorators, which modify or enhance functions without altering their core logic. Understanding these concepts is crucial for leveraging Python's full potential in software development. Understanding Python's treatment of functions as flexible objects is crucial. Functions can be assigned to variables, passed as arguments, and returned from other functions. This flexibility allows for powerful manipulations, setting the stage for mastering decorators. These capabilities enable dynamic and reusable code structures, enhancing the efficiency and readability of Python programs. In Python, functions are first-class citizens. They can be assigned to variables, passed as arguments, returned from other functions, and stored in data structures. For example, assigning a function to a variable allows it to be called later, while passing it as an argument enables dynamic execution. This flexibility is foundational for advanced concepts like decorators. Inner functions, defined within other functions, create a nested structure with hierarchical scope access. This allows inner functions to access variables from their enclosing function's local scope, enabling powerful programming patterns. For example, in the code provided, the inner function prints a message using a variable from the outer function's scope. Closures occur when an inner function retains access to its enclosing scope's variables, even after the outer function finishes. This allows stateful functions, as seen in the counterexample, where the increment function maintains the count variable. Closures enable encapsulation, data privacy, and form the foundation for decorator patterns. Decorators in Python are a powerful tool for dynamically altering function behavior. They enable developers to enhance or modify functions without changing the original code, ensuring clean and readable code. This elegant feature promotes separation of concerns, allowing for more modular and maintainable software development. A Python decorator is a higher-order function that takes another function as input and returns an enhanced version. It allows you to extend or modify function behavior without altering the original code, promoting separation of concerns. Imagine it as gift wrapping, enhancing presentation while preserving the core function. Understanding a decorator's anatomy is crucial. It consists of an outer function that takes the target function as a parameter, an inner function defining additional behavior, and a return statement that replaces the original function. This structure allows seamless enhancement of functionality, as demonstrated in the start_end_decorator example. The syntax in Python simplifies decorator usage by applying the decorator at function definition time, enhancing readability and maintainability. Unlike the traditional approach, which requires reassignment, the syntax executes the decorator immediately, making the code more concise and Pythonic. Creating robust decorators involves understanding function signatures and ensuring flexibility. Use *args and *quargs to handle any number of arguments. This approach allows decorators to wrap functions seamlessly, maintaining their original functionality while adding new behavior. Properly implemented, decorators enhance code modularity and reusability, crucial for production environments. Decorators must handle diverse function arguments using *args and *quargs. The log arguments decorator captures function calls, printing positional and keyword arguments, and the return value. For instance, multiplying 5 and 3 with an operation keyword results in detailed logs, ensuring decorators accommodate any function signature seamlessly. Decorators can enhance functions by adding pre/post behaviors while ensuring the original function's result is returned. This is crucial for maintaining expected functionality. For instance, a timing decorator measures execution time and returns the function's result, as seen in calculateSum, which computes the sum of a range efficiently while logging execution time. Using decorators can obscure function metadata like name and docstring. By applying at functools.wraps, we preserve this metadata, ensuring the function's identity remains intact. This is crucial for debugging and introspection. For instance, without @wraps, greets metadata is lost, but with @wraps, it retains its original name and docstring, enhancing code clarity. Decorators are invaluable in production, offering practical solutions for software development. They enable logging, authentication, and caching, enhancing code efficiency and maintainability. By wrapping functions, decorators streamline processes, making them essential tools for developers aiming to optimize application performance and reliability. Logging decorators are essential for tracking function calls and debugging. By wrapping functions, they log inputs and outputs, providing insights into application behavior. For instance, the add numbers function logs its invocation and result, aiding in efficient debugging. This approach centralizes logging logic, ensuring consistent and reusable tracking across multiple functions. Access control decorators enforce security by checking user roles before executing functions. For instance, a function like delete user requires an admin role, ensuring only authorized users can perform sensitive actions. This approach centralizes access control, enhances code reusability, and clearly defines security requirements, minimizing code duplication and potential vulnerabilities. Memoization significantly enhances performance by caching results of expensive function calls. This is particularly effective for recursive functions like Fibonacci, where previously computed results are reused, reducing computation time. For instance, calculating Fibonacci 35 is fast with caching, whereas without it, Fibonacci 40 would be considerably slower, showcasing memoization's impact on efficiency. Timing decorators are crucial for profiling code by measuring execution duration. They help identify bottlenecks and validate optimization efforts. By wrapping functions, they capture start and end times, calculating elapsed time. For instance, a slow function wrapped with a timing decorator reveals execution time, aiding in performance analysis and improvement. Mastering advanced decorator patterns involves understanding the order of application. In Python, multiple decorators can be stacked on a single function, applied from bottom to top. For instance, using @italic and @bold on a function wraps the output in I and B tags, respectively, demonstrating the importance of order in achieving desired formatting. In Python, stacking multiple decorators on a function is possible, with the order of application being crucial. Decorators are applied from bottom to top, or inside out. For instance, applying @italic and then @bold to a function wraps the output in I tags first, followed by B tags, resulting in a bold and italicized text. Decorators can be configured using a decorator factory function. The outer function accepts parameters, like times equals 3, and returns the actual decorator. The middle function is the decorator, taking the function to be decorated. The inner function, or wrapper, executes the logic, repeating the function call as specified. For example, greet Alice prints hello Alice 3 times. Forgetting to return the result in a wrapper function can lead to unexpected none returns. Always use @functools.wraps to preserve function metadata. Handle arguments with *args and double *quargs for flexibility. Remember, decorators apply bottom-up. Test stacking order. Debug by printing function names, using help, adding logging, and setting breakpoints in integrated development environments. Decorators enhance readability by clarifying code intentions and reducing clutter. They maximize reusability, allowing a single decorator to be applied across multiple functions, embodying the don't repeat yourself principle. By separating concerns, decorators keep core functionality distinct from auxiliary tasks like authentication and caching, improving maintainability and centralizing common patterns for easier updates. Explore RealPython's comprehensive tutorial for interactive examples and advanced patterns. Geeks for Geeks offers a step-by-step guide with visual explanations. Refer to Python Enhancement Proposal 318 for official specifications on decorators. Engage with online exercises to test your understanding and master decorator patterns, edge cases, and best practices in professional Python development. Challenge 1 involves creating a decorator to log function calls with timestamps and execution duration. Challenge 2 requires a decorator to handle specific exceptions gracefully, logging errors without crashing. Challenge 3 focuses on implementing a rate-limiting decorator to control function call frequency. Consider how these challenges enhance code organization and explore creative uses for decorators.